So this is Jungwon Kim from Korea University. Today I'm gonna make a presentation for WCCI tutorial. So in this tutorial, my focus is in federal learning. Okay. So today the tutorial title is Introduction to Distributed Quantum AI, Neural Networks, Reinforcement Learning, and Multi-Agent Systems. In federal learning, we are talking about the distributed learning. That's why in distributed quantum AI, in this session, I would like to briefly introduce what is the quantum federated learning. Before starting, let me introduce the characteristics of my presentation. First, I would like to introduce the basic concept of quantum neural networks and quantum reinforcement learning with the minimum amount of the mathematics. So you don't need to worry about too much, even though you are not familiar with the quantum mechanics. So you don't need to give up too early, okay? Second, I would like to let you know when we can consider quantum reinforcement learning for our research problems and when we have to avoid it. So I would like to emphasize that quantum reinforcement learning is not an almighty solution. First, I would like to introduce the basic concept of quantum neural networks. And then in section 2, I want to introduce quantum distributed learning because in this tutorial, it's talking about distributed quantum AI. And next, I would like to introduce the applications. And lastly, I would like to make a conclusion. This slide shows the basic neural network architecture. When you have an input, you will gonna have a first hidden layer. In the first hidden layer, you will gonna do the linear combination with the weight factors. You're gonna do the addition of the biases. And then you take the activation function and you can get the result of the first hidden layer. And the result will go to the second hidden layer. And similarly, we will gonna do the weight vector multiplication and bias addition. And lastly, you're gonna do the activation function application. And lastly, you will gonna get this result for the second hidden layer, and this goes to the output layer. When you go to output layer, you're gonna do the same thing. You will gonna do the multiplication with the weight factor, and you're gonna do the addition with the bias. Lastly, you're gonna take the activation function, and you can get the final result. This is the end-to-end pipeline for the conventional deep neural network architecture. This procedure is very similar to the linear interpolation. So let me introduce the interpolation briefly at first. So when you look at the illustration, just like that, in the left, as you can see in the left-hand side, you have three samples. 1, 10, 2, 15, and 3, 40. So since you have three samples, we're gonna define a second order polynomial. Okay, so when you have 100 sample, then you can define 99 degree polynomial, right? The polynomial exists. So when you look at the right hand side, you can see the second order polynomial. Then you have to find the coefficient. How you can do that? You will put 1, 10 into the equation. Again, you will put 2, 15 into the equation. Lastly, you will gonna apply 3, 40 into the equation, and you can get the list of the linear equations, and you can solve the system using Gaussian elimination. Then you can get the result for the coefficient. That is the solution approach for this given interpolation problem. So why this is related to neural network training? Because the reason is that when you carefully look at the matrix-based mathematical structure of neural network architecture, you can realize that it's kinds of the interpolation procedure. When you look at this illustration, as we introduced before in the first slide, when you have input data, you're going to do the multiplication. So when you have the input data here, you're going to do the multiplication with the weight, addition with the bias, take the activation, the result will go to the second hidden layer, and multiplication with the second hidden layer weight factor, addition with the bias, and lastly, and then you will take the activation function. And this result will go to the output layer, and multiplication with the output layer weight factor, addition with the bias, and take the activation function. So this is kinds of the equation what you have. Even though it's not polynomial, it's kinds of the structure what you can see. So once you have this structure, when you put a lot of data on top of this one, then you can find the coefficient, blue coefficients, and then you can determine the exact function. That's why this is called functional approximation. Then here we have to realize that what is the quantum neural network. So today we're gonna talk about quantum neural network. So what is the quantum neural network? So these kinds of those mathematical procedure will be done again in quantum domain. So up to now, our mathematical results are all real numbers. So we have to do the same thing over quantum domain. Then we can design the quantum neural network. In addition to that, so what is the meaning of this multiplication and addition? This is kinds of the transformation. When you have the input data, you are doing the transformation multiple times and you get the result, right? So this is kinds of the transformation. So what is the quantum neural network? You are doing the same procedure in quantum domain and you have to define the transformation, then you can define your own quantum neural network. Okay. So in order to understand the quantum domain very briefly, so I get this illustration. So in classical bit operations, you have 0 and 1 only, okay? But if you are considering the qubit, which is called quantum bit, so then you can assume these kinds of 3D sphere, which is called blue sphere. So you have 0 and 1, and your data is existing on the surface of the 3D sphere. So that can be identified as the complex number. Okay. Then you can identify the position of the value as a complex number. Once you are doing the measurement just like that, then this can go to 0, this can go to 1. Okay. So when you add up the information more and more in here, then you are doing the superposition. This is the brief concept of the qubit calculation. Okay. Then what is the transformation then? Transformation is called uh, rotation in the 3D sphere. So in the 3D sphere, you are doing the x-axis rotation, and then you have y-axis rotation, you have g-axis rotation. So you can define the transformation in the linear domain. So with this rotation gate in 3D sphere. Since we are talking about the qubit on top of the 3D sphere, we can define our rotation as 3D position changing gate over x-axis, y-axis, g-axis. That's why these kinds of gate can be used for the transformation. So you are doing the rotation gate over x, so x of sub x, r sub x. You are rotating over y-axis, that's why this is called r sub y. Lastly, you are doing the rotation over g-axis, that's why this is called rotation sub g. So this is another rotation gate for g-axis. If you are rotating in 180-degree, so then this is called Pauli gate. So this is, if your center is 180-degree, then this is called Pauli X gate. If your rotation over y-axis is 180-degree, this is called Pauli Y gate. Lastly, you are doing the rotation 180-degree over g-axis. This is called Pauli G gate. Okay. So lastly, when you are doing the mixing of the information together, then you are using the entanglement gate, which can be denoted as a CNOT gate. Okay. So you are using these kinds of the rotation gate. So finally, you can define this end-to-end pipeline for the quantum neural network. Let me briefly introduce this one, okay? So when you have the input data, you have to do the translation into quantum domain. So this is called state encoder. You are encoding the state. That's why this is called state encoder. So when you have real number data, first you are translating everything into the quantum domain. So that's why you have a unique position over 3D blue sphere. Okay, this can be denoted as axis. So the training value is the angle over x, y, g axis. Okay. Now, when you get into this data into the hidden layer, your hidden layer will be defined as the transformation. That's why you have x-axis rotation, y-axis rotation, and z-axis rotation for every single time. So in this quantum neural network system, you have 4 qubits. So in this 4 qubit, for each qubit, you are rotating x, y, g axis. Okay, this is same, this is same, this is same. And right after that, you are mixing the information using entanglement gate or CNOT gate. So you are having a CNOT gate right after that. So this is one hidden layer. So you are doing this procedure multiple times. That's why you have multiple hidden layer component. And eventually you have the measurement in order to fix your value into 0 and 1 by collecting the quantum state. So that's why you have the measurement in the end. So this is end-to-end pipeline for the quantum neural network system. Okay, so once you define this quantum neural network, you have to understand what is the benefit of this system. So from now on, I will going to introduce what is the advantage of quantum neural networks. All these advantages are well summarized in the paper, as you can see below. So Suyang Park, J J. Kim and C. Park, S. Jung and J. Kim. From our lab, we wrote down this paper. So this is for the introduction to the quantum advantages when you are using quantum neural network for the reinforcement learning. So this is published in IEEE Communication Magazine. You can now download it. You can read it if you want to understand further. Okay. And the first advantage of this system is the faster training. So in conventional neural network, as you can see below, it has the cost function in the end. You are doing the gradient descent in order to minimize the cost function. So while you are doing the minimization of the given cost function, you are doing iterative optimization because you are using the gradient descent. So while you are doing the iterative computation over there, you have backpropagation every single time. But in this case, after the measurement, your states are collapsed. Every single value will go to 0 and 1. And then you cannot see any evidence in order to find the previous value before the measurement. That's why backpropagation is not working in this time. So how you can do that? You have to use the another methodologies that is called the parameter rule or the others. Those are all based on the search-based technique, just like Newton's method. That's why we are not doing the iterative computation. That's why it is much more faster than the previous classical neural networks. Okay. And then let's look at the next advantage. So suppose that you are using this neural network for the reinforcement learning algorithm. Then after the measurement, you will get the value 0 and 1. Then you can imagine that this can be very useful for the scheduling problems. In the scheduling problems, when you have the area just like that, this is 4 by 4, and then this can be 0, this can be 1. 1 means that this region, this space is scheduled for service. Zero means that this region is not scheduled for service. That's why after the measurement, the value will be the 0 and 1. That's why this will be the good indication for the scheduling vector. That's why after the measurement, your values will be 0 and 1, and this will be used for the scheduling. But if you are not using quantum-based algorithm, you have to find 0 and 1. This is kind of the integer programming, which is combinatorics. So when you are considering combinatorics, your complexity is NP hard. But that's why in this case, you have to do the combination. That's why you have the such space as 2 to the 16. But when you are allocating qubit every single space and you are taking the measurement over there, and then you will get 0 and 1 automatically. That's why you have only 16 number of computation. That's why 2 to the 16 to the 16. You are doing the reduction of the complexity as a log scale. So that is one of the benefits of the quantum neural network while you are using this one for the reinforcement learning. In reinforcement learning, when you have a large scale action space in the end, your convergence can be hard. So that's why when you can compress your output space and then action space, then you can have much more chance to get convergence. That's why this is much more beneficial in terms of the convergence. It means that even though you're higher space in the action space, while you're when you are using the quantum neural network, you can have much more chance to get the convergence. That's why this is highly scalable. So much more detailed mathematical background were introduced in this paper, as you can see below, ACM CIKM paper. So much more mathematical details are discussed in the paper. The last advantage is very straightforward. So when you are using the quantum neural network, you can utilize much more smaller number of parameters, training parameters. That's why that is very lightweight. Okay. So up to now, we can see three different quantum advantages when you are using quantum network. First, the training is fast. Second, it is very scalable. Lastly, it is lightweight. That's why we are using the quantum network. Okay. So this is the illustration which shows the advantage of the quantum reinforcement learning. So when you have larger such space, action space just like that, this is 2 to the 16, which is the scheduling result when your such space is 16. So the action dimension is 2, which means that this is 2 to the 1. Action dimension is 16, this means that you have 2 to the 4. So it means that for the first graph, in this one, that is, it has only one space, you are doing the scheduling. Scheduled or not scheduled. That's why you have two dimensions. For the second one, in this case, you have four spaces and you are doing the scheduling combination. And then you have 16 different combinations. That's why you have four spaces. This can be denoted as 2 to the 4. So lastly, you have 16 spaces and you are doing the combination. That's why you have 2 to the 16 number of such spaces. You have these three different type of system. For the first one, which is the most simplest one, so in this case, you have only one space, you are doing the scheduling decision. You are scheduling or not scheduling. So in that case, conventional reinforcement learning algorithm is better than the quantum because you are not doing the encoding, you are not doing the compression. So in the quantum, as you can see, in previous quantum neural architecture, we used only 4 qubit. The reason is that in modern quantum computing systems, we are on the NISQ. NISQ means that noisy and intermediate scale quantum. Noisy means that individual qubit computation still has some errors. Intermediate scale means that the number of qubit is not sufficient. That's why you have to do the compression. Due to the compression, the performance of the quantum-based RL is slightly lower than the conventional one, SOTA. So if the problem is simple, and then using the conventional one might be better. This illustration shows that. The second one is saying the same thing. So when your given problem is very simple, when you four spaces, you are doing the scheduling, then the problem is simple. If your given problem is simple, you don't need to worry about the quantum because quantum has some compression, it has the information loss. So in this case, SOTA is better. But lastly, when your problem is very complicated, you cannot converse with SOTA is conventional reinforcement learning. The only one solution is quantum-based MARL. Okay, so based on this result, what I want to say is that if your given problem is simple, you don't need to use quantum-based algorithm because it has some information loss. But if your problem is so complicated, you cannot solve this one in conventional reinforcement learning algorithm at all due to the convergence problem, then quantum RL is only one solution you can take. This is very important. So if your problem is simple, you don't need to worry about it. If your problem is so complicated, you should use the quantum reinforcement learning, which is only one unique solution. You can make this problem converse. Okay. So in the first slice, I told you that quantum is Almighty solution. Sometimes it's not good, sometimes it's good. This one shows that. Okay, if your problem is so easy, you don't need to worry about that. Okay, if your problem is so complicated, which is very hard to converse using conventional one, then you have to try the quantum reinforcement. This slide is talking about that. So based on that, we have to go to the discrete computation because our topic today is the quantum discrete learning. So we are talking about the federated learning. You have the global server here, and then you have individual local devices. Then based on the data and models in individual computing devices, you want to make the global model. That is called federated learning. Okay. In this federated learning architecture, the data resides on user devices and client train model individually. And then the trained parameters are delivered to the server. and then server will get everything, and then server aggregate and update the global model. And then lastly, the updated model will be distributed to the client. Why we are doing this one? This one is doing due to the data privacy. So suppose that A has A's own data and A made its own model based on that. And then the model is delivered here. And this model is delivered here, and delivered here, and aggregate everything and then distribute and update the model. Then even though A cannot see any data in the other devices, B, C, or D, and then A can get the model which is trained or made based on the other data. That's why even though they are not mixing the data at all, they are not sharing the data at all, we can have global model. So this is the benefit or reason why we are using the federal learning. Okay. But federal learning still has some problems. So challenges of federal learning is that non-IID problems because data is not fully unique, fully and well distributed. Sometimes the data is fully focused on device A. Sometimes device D has nothing, and then it has no reason, no data to make the training. That's why data imbalance is very big issue in quantum federal learning in general. So this is talking about that. If your distribution is not that good, and then your some of the device has poor performance, then in this case we have to eliminate that kinds of device in order to guarantee the high performance in the global model. Okay, this is one issue we have to try to solve in general quantum federal learning, not only for the quantum federal learning. Okay. Then here we need to talk what is the quantum federal learning. So we already talked about the basic concept of the federal learning, and in this case, we are talking about the quantum federal learning. In this case, individual model in ABCD, it has quantum neural network, and then it is quantum federal learning. It's easy, right? But in this case, we have two types of the quantum federal learning. The first one is that the delivering the parameters for ABCD will be quantum state. That's why the deliberation of this channel will be quantum channel. Then you have to use the quantum teleportation, which is the technique for the transmission of the quantum state between two separated machines. That's why you have to use the quantum channel, and then you have to deliver how you can deliver the quantum state over quantum channel. So this is one thing you have to try, you have to consider in quantum federal law. Okay. Uh, uh, when I start to introduce quantum federal learning, I told you that we have two types of the quantum federal learning, right? The first one is the quantum federal learning, which is using the quantum channel. The next one is the quantum federal learning, which is not using the quantum channel. In that case, every single devices, they will go to do the measurement, and they want to do the and all the quantum state will be collapsed, and then right after that you find the angular values and you deliver the angular values each the server, and you get the global model. That is the case where you are not considering quantum channel. So you have two different type of the quantum federal learning here. And as you can see here, why so there are a lot of benefits in quantum federal learning. The first one is the privacy preserving. Since you are not mixing the data among the distributed devices, you can keep the privacy for individual data. And parameter efficiency. As I introduced before, in quantum neural networks, you are saving the number of parameters. That's why it is lightweight. This is another benefit in quantum federal learning. Lastly, quantum advantages. So as I presented before, we have quantum advantages when you are using the quantum neural network uh, rather than deep neural network conventional format. That's why you can still utilize the quantum advantage when you are using the quantum federal learning. Okay. So since we understand basic concept of the quantum federal learning, let's move to the quantum algorithm. So in this case, as I told you before, in the channel, when you are not using the quantum communications here, then if the channel is poor or if the channel is good, depending on the channel state, you have to consider that kinds of behavior. So as you can see below, uh, device one, device two, you have two different devices. You want to make the global QNN model using the federal learning. In this case, when you look at the left-hand side, the channel is good. That's why you can deliver all the parameter values into the federal learning server. However, when you look at the right-hand side, if the channel is poor, then in that case, you cannot deliver everything. Then you have to deliver certain amount of the parameters depending on the channel state. That's why you have to control the number of the parameter delivery. Okay, this is one thing you have to try to consider. So this is also talking about the same thing. So when you have the quantum neural network architecture, you have three different layers, CU layers. So if the channel is good, you can deliver everything. Your channel is not that good, then you cannot deliver this one. Okay, then how you can do that? So first of all, in the individual devices, you have to design your neural network which can control the number of parameters. And then depending on the channel, if the channel is not good, then you will deliver small number of parameters. If the channel is good, you can deliver a lot as much as possible. So you have to control the number of parameters when you are designing individual neural network architecture. So how you can do that? The designing philosophy is presented in the next slide. Here, when you are doing the training, so you are doing the measurement, every single layers, then you are training the parameters based on that. So in this case, if you have your channel is not good, then you have to deliver only this one. That's why you are doing the measurement here. If the channel is very nice, then you can deliver as much as possible. Then you have to pass everything. Then you are doing the measurement in the end. So then you will get the parameters for individual three layers. Then you can deliver three times, comparing to the case where you have four channels. So these kinds of the architecture is called adaptive quantum neural network. Since you can design adaptive quantum neural network, you can adapt the number of parameters depending on the channel. Okay. So this is adaptive architecture for the quantum federal learning. So when you can use this one? So in the drone or in the mobile systems, the channel is not good every single time. So in drones, they are flying in the sky. So sometimes the link is safely connected. Sometimes they are broken consistently. That's why your channel is time varying every single time. So depending on the channel, you have to control the number of parameter transmission. That's why in this case, you can consider quantum federal learning under adaptive channels or under adaptive control architecture in individual quantum neural networks. Okay. So this shows more detailed illustration about that. So this is also talking about that. So let me skip this one. So lastly, let me show you the applications. The first one is the IoT. So in IoT devices, we are carrying IoT device every single time. Your glasses, your cell phone, your watch. These are all IoT devices. So then you can use quantum federal learning systems into these IoT devices. If the quantum qubit uh, manufacturing technologies are innovating. So that's why our hand carrying devices has qubits eventually, then you can use this system. The next one is healthcare applications. In healthcare applications, using quantum federal learning is very beneficial because you have to guarantee the high performance computing in order to much higher performance because medical applications requires high level of the accuracy in AI. That's why QFL will be very useful for the high performance computing capabilities in medical systems. So next one, smart grid dynamic security. So even smart grid or their related society in energy IT, nowadays they are talking about the quantum computing a lot because quantum computing can be useful for large scale scheduling or large scale data management or large scale data training. That's why quantum tech related technologies are widely or actively discussed in this research domain. And then, so metaverse, these kinds of the system, or digital twin, these kinds of system is also considering quantum computing because these kinds of metaverse or digital twin will be also used for the physical AI or world models or something like that. Because in the virtual environment, you are doing the training based on the physics models or generative AI, then uh, this is called a world model. Based on that, you can do the training and you want to apply this result into the physical world. That's why physical AI also related to this topic. So in order to realize this one, you need a lot of computing capabilities. That's why quantum federal learning also considered in this system. So let me make a conclusion for this presentation. So first, we briefly introduced quantum neural network architecture without serious mathematics. I just introduced what is a quantum neural network based on the conventional neural network architecture. Right after that, I also introduced what is the quantum federal learning uh, based on the based on some basic scenarios in general quantum federal learning. In addition to that, I introduced the adaptive quantum neural architecture, which can also used in quantum federal learning. Lastly, I introduced several applications. Okay, in future work, from now on, we may need to consider software engineering technologies because since we have a lot of innovation in algorithms, we want to realize this technique in real world. That's why software engineering related methodologies are required for the quantum neural networks. That's why this is very important. And then our lab has also planned for the quantum computing plus generative AI, which is widely considered in the literature. Lastly, we need to think about much more various applications. So if you want to understand much more details about quantum AI or quantum neural networks, please drop by our research lab website and see more research, and you can realize what's going on. Okay. And here, this is the list of the top conferences what we have in our lab. So if you have interest on this one, then you can find some more papers here. And then quantum CNN, these are all used for the much high scale level of computer vision applications. Then you can read over the paper from the list. And this is the reinforcement learning based algorithms. So we are using the reinforcement learning algorithm for many applications, such as satellites or aerodynamics, networking, and much more multimedia systems. So these are all related to that. So if you have some more interest on this topic, please refer to the papers. Lastly, this time we introduce quantum federal learning. There are some more research results are listed in this slide. And lastly, I would like to introduce the software engineering. Since we have some innovation in algorithm, we need to do the software implementation. That's why nowadays our lab also working on the software engineering research results in quantum federal learning or quantum neural networks. And this is the end of my presentation. If you have any questions for this one, please email me and I can answer to you one by one. Thank you very much for your time today. And let's finalize my presentation here. Thank you. Let me finalize my presentation here. Thank you.